Well, good evening. My name is Joe Damji. Welcome to the Bay Area in-person meetup. This has been a while since we had an official Ray area meetup. How many brilliant? Well, welcome. Delighted to all of you to actually be here. How many of you actually have used Ray before? Heard of Ray before? Okay, well, you can stay, please. Well, thanks you for coming. I'm sort of moderating the meetup today, and we have actually a good agenda today. We have about 3 talks. I'm going to go very briefly about the upcoming announcements, what's actually coming and what's actually happening in the Ray community. And then we'll have 3 talks, one from Amol Kamsethi. Now, those of you who actually are working in the machine learning, you know that batch inference is really central. It's one of the very common workloads. And today, with the size of the models increasing and the size of the compute, you actually need to do batch inference at scale. So Morg is going to talk about what are some of the challenges that you actually have to deal with when you're doing batch inference at scale. What are the existing solutions available for you today? And how does Ray fit in the grand scheme of things, and probably demonstrate that probably it is one of the, in an opinionated way, the best solution available for you to do batch inference at massive scale. And then very much similar to what Morgan is going to talk about, we're going to have Eric Liang, who's also one of the committee on Ray, and he's going to talk about how you can actually use Ray data to saturate both your CPUs and GPUs. And today, when you're doing batch inference, especially when you're dealing with images and when you're dealing with sound and video recordings, you tend to use both your heterogeneous cluster. You have your CPUs and you have your GPUs, and you want to make sure that you optimize and saturate them when they're actually working together. So you're going to hear about how you can actually use Ray data to stream the data to do your parallel execution. And these 2 talks are very actually related. And then we're going to hear from a Ray developer, a Ray user from Pinterest. And a lot of companies today are actually sort of building machine learning platform on top of Ray. Pinterest is one of them. DoorDash is another one. Uber has actually done the same thing. Spotify has actually done the same thing. So we got all these different companies who are actually building their own infrastructure on top of Ray to expedite their development in Ray. So I think that's going to be this 3 great talks for you to actually have a good news going to be there for us. A couple of announcements. Just about a week ago, or maybe a week ago, we actually announced our 2.5 release on Ray. Now, Ray 2.0 was announced last year at the summit, and there were actually 3 words that Robert said what Ray 2.0 is going to be about. It's going to be simple, it's going to be steady, and it's going to be swift or performant. And since its release, we have steadfastly committed ourselves with every incremental release to make sure that we actually aim towards our goal. Make it simple, make it scalable, make it easy to use. And this particular release has sort of, keep on going to that particular pillar of our objectives. And you can now do distributed training with Ray Train. When you're actually building large particular models, if the model doesn't actually fit into your one worker, you can actually shard that model across. And when you're doing checkpointing, there's a need for you to actually aggregate all the checkpoints on one central place and then load it up to somewhere where you actually want to store it. It turns out that that's not the optimal solution, because you can either run out of memory because you got all these checkpoints coming in across, and you can also increase the bandwidth on the network. So the solution is to actually do distributed checkpointing, where each and every modal worker will upload and store the checkpoint in a local storage. Likewise, well, you don't put it in. Ray Server has the ability now to serve LLM models at scale. And one of the things when you actually do inference on LLM model, you actually notice to see that when you type in a prompt and you send it an inference, it might take 5 seconds, it might take 30 seconds. And you're just waiting there for the prompt response to come in. Well, one way to actually give you a better user experience is to have your tokens or the next word being streamed back to you. So one of the support we have actually added in Ray Server is to do streaming response. So now you actually get the streaming response right away as the LLM is actually computing what's the next generated word. So you actually get the feedback, something very similar to what you see in ChatGPT or one of the advanced proprietary model. So you get this good user experience. So that's one of the things that you can actually do with Ray Server. And then one of the things we actually added was In the earlier version of the release, you couldn't do multi RL agent training on multi-GPU and multi-machine. So that has been sort of added, and that sort of gives you a good advantage if you're when you're doing reinforcement learning. And finally, what you're going to hear about today, what are some of the performance enhancements you can actually do on Ray at batch inference at scale. So that's in 2.5. We have a blog out there. You can actually talk about that blog. Now, talk about LLM. A couple of months ago, we actually released this thing called Aviary, which is really an open source way of exploring what the models are out there. So if you're new at LLM and you want to figure out what are some of the open source models, what they look like, how long would it actually take me for doing inference, we have this Explorer browser, which is a front end that gives you the ability to actually choose a particular model that you actually want. So you can choose any one of the LLM models that you want, open source models, which are hosted on Hugging Face. You provide a particular prompt to it, whatever prompt you actually want, and then you do the inference, and it actually gives you the 3 prompts based on the respective models. And you can now compare which was actually best model and which was the worst one, how long it actually took, and how much it actually cost. So if you're browsing through open source models, you want to figure out whether your prompt or your particular use case, choose a particular model that we actually have, and you'll be able to do that. Currently, it's open source. We also have the ability to host you on particular models. That's down the line. You can actually find out more information about that, or go to aviary.com. So talking about LLMs, we have another meetup here tomorrow. House full of great lineup of speakers. We have a co-founder and co-creator of Ray is going to be here. Harrison Case, who's known for LangChain, is going to be here as well. Michael Tricote is the founder and CTO of Airbyte, and he's going to talk about how they actually use private data to host on their Airbyte workflow. And then the creator of Vicuna from UC Berkeley, Jiang, is going to be here, and moderated by Charles Fry, who is one of the co-founder of Full Stack. So good meetup tomorrow. Hope to see you guys here. I think it's house full, but there's always room for more. If you're interested, anybody been to Ray Summit? Okay, maybe this is the first time is a good way. We have Ray Summit coming up in September. This is early registration, so if you're interested to find out how people are actually using Ray globally, what are some of the interesting use cases they're solving, it's great to actually have that. We had this Ray Summit last year. It was a huge success. We had people from all around the world. We expect to have twice as many people, twice as many training sessions, so please do feel free to join us in a couple of months to find out everything about Ray. And we have a lineup of community keynote speakers from these luminary companies who are going to share about not only how they're actually using Ray at the company, but also what is the future of distributed computing. Great line of speakers, so good investment for you to know about where Ray is actually heading in the future. 2 books on Ray, if you're interested to find out. They're available on Amazon. This particular book is written by the committers over here, and that one is written by Holden Corral. She's one of the early advocates of open source, and so she's one of the authors as well. They're all available. Feel free to get them if you want to have more about Ray. And then finally, we hold these meetups on a regular basis, both online as well as in person. There are various ways for you guys to join us. You can subscribe to any one of the channels. I'm normally on Discuss quite a bit, answering questions. We have Twitter, do follow us. And if you want to speak and you want to share about your year journey, please get in touch with me, and we'll definitely have you as one of the speakers over here. Now, I'm obliged to put this on front. Normally, when we actually have this particular meetup, we actually have a code of conduct. We are obliged to show that. I'm not going to read all that for you. You can probably just scan it. And this is nothing but more than making sure that this is not a harassment thing for us. So welcome, and I'm going to have our first speaker, Amog, who is a software engineer here at Nscale for the longest time. He's one of the committers of Ray. He's been here for a long time, and he's got his footprints all over the GitHub. So warm welcome to Amog.
Hey everyone, thanks for coming today. So I'll be giving the first talk, and basically this talk is going to be setting up the problem that one of the problems that we're trying to solve here, and it's this particular workload offline batch inference. And in particular, we're going to be taking a look at a few different approaches and comparing how Ray fares against Spark, against SageMaker batch transform. So a little bit about me, as Jules mentioned, I'm one of the developers here on the Ray team. I've been working on developing Ray for 3 years now. I've been working on Ray this entire time in a few different areas, just model training, and then now focusing on offline batch inference. So just an overview. We're going to first go over what is batch inference and why does it matter. Some of the challenges that people face when actually trying to productionize batch inference and scale this out to large data sets. We're going to take a look at exploring the current solution space for this problem and compare 3 solutions in particular: SageMaker batch transform, Apache Spark, and Ray datasets. So first, what is offline batch inference? And overall, it's pretty simple workload, right? You have some pre-trained model, and you want to get predictions from that model on some data set. And this differs from online inference in that requests are not coming in live. You have your input data sets already predefined, it's already available, and you have that already available for you to do inference on. Right? So when you want to do this at scale across hundreds of gigabytes or terabyte level size data sets, this essentially looks like a very simple batch processing problem. Right? You basically map your pre-trained model over this big data set to get your predictions. And this kind of workload is especially relevant today, especially with the rise of foundation models and being able to do zero-shot inference. So without even needing to train models, you can actually get very high quality prediction from these pre-trained models. Or even just generating embeddings, which is common, which is actually very useful for building LLM applications. Again, generating embeddings is a batch inference problem. So what are some of the challenges with doing this at scale? I think the first one is very common is how do you actually manage your compute infrastructure, right? So you have gigabytes or terabytes of data, you need to scale out this computation, this batch processing. Okay, so what do? You need to create multiple machines. These machines need to have CPUs and GPUs, and you want to manage these. And in particular, you may also want to manage heterogeneous compute infrastructure. And what this means is that you may want a cluster where not every node of that cluster is the same type. So this could be useful for certain types of workloads, particularly ones that are very memory constrained. So you don't want to be using expensive GPU. If the bottleneck in your workload is memory, like CPU memory, you don't want to be using expensive GPU instances to address that problem. You'd rather use just the GPU instances that you want, and the remainder of the instances can be pure CPU, the much cheaper CPU instances to address that problem. The second challenge is, okay, now that you have this cluster, you have all these CPUs and GPUs, how do you actually write your software to utilize all the resources in the cluster? And I mean, this is primarily the challenge here is how do you keep your GPU saturated, right? I mean, so this is the most expensive part that you're paying for. And if you're running your batch inference jobs at high frequency or at a very large scale, you want to make sure they run quickly, they run cost effectively. And to do so, you need to make sure the resources in your cluster are fully utilized. And you're not basically paying for anything that's not being used. Third challenge is how do you facilitate this the transfer of data from your storage, whether it's cloud storage or disk, to CPU RAM for preprocessing and then to GPU RAM for model inference. And finally, the fourth challenge is, okay, how can you actually develop very easily, right? So how can you build these pipelines in a way that you can iterate quickly, develop quickly, and there's not a large gap between what you're doing during development and what you actually put into production at the end. So these are the 4 main challenges that we've seen that people run into with batch inference. And if anyone else has anything to also be happy to chat afterwards as well. But from what we've seen, these are the 4 primary challenges. So what does the industry recommend as the solution to this, right? So what are the common problems, or those are the common problems that we saw, what is generally the common solutions that people recommend? And I think this Twitter thread in particular pretty much sums it up, right? So this is Ben Hammer, he's a creator of Kaggle, and he's just posted, hey, I want to spin up a cluster of GPU instances to do some batch inference job. Supposed to be very easy. What's the best approach, right? And you can see there's quite a larger variety of responses. So one guy very confidently just says AWS batch. And you can also try Modal Labs, or Lightning AI apparently handles this well. You know, do it yourself, this guy says, or use Kubeflow with AWS Spot instances, or Azure Batch Compute, or this one guy even says, hey, let's use Ray Serve. Overall, quite like, it's like pretty all over the place, right? There's not any real solution that addresses these challenges well. And sort of what people have found out is like, you may do this all yourself. You may use like this mishmash of like different solutions. Each people have their own thing that they want to use. And we can categorize these solutions into like 3 different categories. The first one is just general batch services. So think about it like AWS Batch, GCP Batch, or Azure Batch. And these handle challenge number 1, right? They provide an easy way to manage your infrastructure, to spin up clusters, create nodes. They don't necessarily allow heterogeneous clusters. So I think for AWS Batch, all the nodes need to be of the same instance type. And they don't really handle challenges 2, 3, or 4, right? Like you can create these clusters, you can submit jobs, but you as the user need to write your software in a way that can fully utilize all these resources, can actually read data from storage, can actually transfer data from CPU RAM to GPU RAM. And development is also not very easy with these solutions. There's another one like Modal Labs, which does make the development very easy and provides some like basic primitives for parallelization, but again, it's not really tailored for this particular use case of batch inference. The second category that we see people use is actually like online inference solutions, right? So solutions that are meant for being deployed as like online services, and they've just use that for the batch case as well, right? And it's like overall pretty simple. You know, this might be a straightforward way if, you know, because you already have your online inference stuff, okay, let's just like use this for batch inference as well. But there's some issues here, and it's primarily because it adds like a bunch of unnecessary complexities for the offline case, right? Like you have to start an HTTP server, you're sending requests over the network, a lot of additional overhead that you don't really need for what should be a simple like map job, essentially. Right, and all this makes it very hard to saturate your GPUs in your cluster because of all this overhead. And in fact, like BentoML, which is one of the common like popular online serving libraries in open source, is like integrated with Spark for this particular reason. And the third approach that what we see is really tailor-made for this workload is just distributed data systems, right? So as we talked about, you know, if you have a pre-trained model, you have a bunch of data, okay, let's just map that model over the data. That's really, you know, for the most part what the problem is, right? So here we're talking about like Spark or Ray data sets. And these frameworks have support for scaling across clusters. You can, you know, they have support for like partitioning your data and batching them as needed. And they also have connectors to a variety of different data sources. They can read from cloud storage and things like that, right? So this category of solutions really is what's most ideal for the batch inference workload, as opposed to like the first 2. So now let's take a deep dive into like 3 in particular: SageMaker Batch Transform, Apache Spark, and Ray datasets. And we're gonna so what we did is we actually benchmarked all 3 of these on an image classification. So very simple image classification benchmark. It's gonna read, we can just see the benchmark here. We have a pre-trained ResNet 50 model, and we just wanna do inference on ImageNet data. And essentially it's 3 steps, right? Read images from S3. We have some very basic pre-processing that's happening on CPU, such as like resizing the images, cropping the images, normalizing the images, and then finally we have model inference on GPU. So you want to create a data pipeline with these 3 steps using those 3 approaches: SageMaker, Spark, and Ray datasets. And we did this on both 10 gigabytes and 300 gigabytes. So here are the results from 10 gigabytes. So we tried a few different Spark configurations, as well as like SageMaker Batch Transform and Ray. And we see that from this, actually Ray datasets outperform SageMaker quite a bit, and then also it's roughly like 2 times the throughput compared against like the best Spark configuration. So I think the first question probably you're wondering is like why is SageMaker Batch Transform so low? Right, it's only like 19 images per second. So the thing with SageMaker Batch Transform is that it fell into the category number 2 that we talked about before. It's like an online inference solution, right? So it's basically using an architecture that's meant for online serving and like trying to shoehorn that into this workload that doesn't really do well in. So it actually starts an HTTP server, it deploys your model as an endpoint, each image is sent as a request to the server, and it has some limitations like it's not able to batch data across multiple files, and there's like a maximum payload size of 100 megabytes. And overall, like this really cannot saturate your GPUs, right? You're not able to batch enough data or move enough data through your pipeline to fully utilize all your GPUs, and therefore your throughput overall is very low. And add to that you have like pretty overall, at least when I was doing it, I found the developer UX to be quite not as easy, and the debugging was quite difficult. You have to start a cluster every time you want to run the job, so it overall made the iterations pretty slow. So that was for SageMaker. Now let's take a look at so what's the difference between Ray and Spark here? So let's compare Ray datasets and Spark. And I think the biggest difference here in performance is that we want to be able to utilize all the resource in our cluster. And what's unique about this particular workload is that it's a hybrid workload consisting of both CPU preprocessing and GPU inference, right? So you have computation that requires these two different sets of hardware. And you need to make sure at any given point of time, both the CPUs in your cluster and your GPUs in your cluster are going to be fully utilized. And this is where one of the advantages of Ray datasets comes in, is that it has basically a very native scheduling support for GPUs. And I think this GIF kind of demonstrates this. So with Spark, you generally have more CPUs in your cluster than GPUs. But what it does, because it doesn't really respect the GPU scheduling, it'll end up fusing all of the different operations together. So it'll run both the preprocessing and the inference as part of the same task. Therefore, you're not fully utilizing your CPUs. However, with Ray, it can independently scale these two steps because they have different resource requirements. So even though we have less GPUs than CPUs in our cluster, we can still scale the preprocessing independently from the inferencing step. And I think the second difference here is that Ray datasets has a streaming execution support, while for Spark it is a bulk execution model. And I think in Eric's talk we'll be going over more of the details here. But as you can see, for Spark, we don't start executing partitions 3 and 4 until 1 and 2 are fully finished. And we get the predictions for those. For Ray datasets, we can actually stream all this data through and take advantage of the Ray object store in order to buffer data in between these steps. So while we're doing inferencing on GPUs for partitions 1 and 2, partitions 3 and 4 can then, we can do preprocessing on partitions 3 and 4, so fully pipeline all the data through. And this is actually this is the primary reason for why we're seeing such a big performance difference with Ray datasets and Spark, is the ability to support the streaming execution model, and also the ability to scale your CPU and GPU stages independently. I think some other differences here is that, as we talked about for challenge number 3, we want efficient data transfer. And for this particular workload, again, one unique property for these type of deep learning workloads is that you want to work with you essentially have large multidimensional tensors, right? So each image is quite large size, generally compared to tabular data, or if we're working with audio data or video data, it gets even larger. So with Ray datasets, it's fully NumPy and PyArrow based. There's no pandas overhead. So that's one of the differences here. And then also Ray datasets is fully Python native, right? So there's no JVM to PyArrow overhead as well. And then finally, with regards to developer experience, overall it's roughly the same between Ray and Spark, but one of the differences here is that Ray is Python first. So a lot of your common Python debugging tools, you can leverage that with Ray, and overall makes for a better, easier debugging, better stack traces, just overall smoother experience. Cool, okay, so that was 10 gigabyte between Ray and Spark. Let's see how this works with 300 gigabytes, and I'm gonna try to show this live. So I have here a Spark notebook, and what it's going to do, so let me just run this whole thing. Yep, so let me just get started with running it, and then we can go over how this exactly looks like. So again, it's the 3 steps that we talked about. You're going to read images from S3, pre-process those images on CPU, and then do model inference on GPU. So we have about 300 gigabytes of images stored in S3 and Parquet files, so we're going to read those, apply some basic pre-processing that we talked about. So these are all PyTorch pre-processing functions, very standard, and then do our inferencing. So what we had here is we just have a pre-trained resonant model. We're going to broadcast this to all these Spark executors. And then we're going to have a predict function here, which is going to take like the next batch, convert it into a PyTorch tensor, do some small manipulation here, pre-process it, and then pass it through to the model to get predictions. So this guy's going to run, and let me kick off the array side as well. So I'm going to run this here. This is this is the AnyScale platform that we have, but both of these like benchmarks can be fully done on open source, and the benchmarks are fully released as well on GitHub. So let me just run this, kick this off, and as you can see, the code again looks exactly the same, except here we're using array data sets instead of Spark. So we have our pre-trained resonant model that we get from PyTorch. We have our pre-process function here. And then we have our inferencing logic is here. And we do this in a class rather than a function, so that we only have to initialize the model just once, and we can reuse that same model across different batches rather than having to initialize the model every time for each batch. Then we just map that over our data set, and we'll get the predictions. So both of these are running right now, and let's see how long these will take. I think in the meantime, if maybe it's a good point to stop here if anyone has any questions or.
What's the essentially time breakdown of time spent in actual computation or
So the question is, what's the time split between what's the inferencing and?
Yeah, let's say what we are actually doing the PyTorch call and whatever else over there comes from needing in the data purpose, streaming everything in the same purpose, that's the time the PyTorch call.
Yeah, I think, so I don't have an exact number off the top of my head, but I think most of the time is coming from the inferencing call for both cases, so, yeah.
Is this one on? Yeah. Any other questions? Yeah.
Yeah. So in the previous the animation which you showed, there was like a ray buffer which was trying to accelerate the. I mean, the difference comes because you're using the buffer, in my opinion. Apart from the fact that you're also parallelly starting work in CPU, even though there's inference going on at GPU. But what is this additional resource with ray buffer, and do you have like back pressure when there's a lot of items in the buffer itself?
Yeah, that's a great question. So I think that will be covered more in the next talk about the details about how the execution model works. But yeah, there is back pressure if you buffer too much data. So we'll limit the parallelism of like upstream operators if that's the case.
Is it like an additional resource? Like, what are the 5 nodes? Is it like an additional node?
No. So yeah, a portion of the memory of each node is used for the shared object store. So it's not an additional resource that's required. Yep. Cool. So I think yep. So these are almost done. Array 1 is still going, and the Spark 1 is still going here. And we should see this should finish in a few seconds. Yep, so we get an overall throughput of like 2,800 images per second with the array data sets. And with the Spark one, this looks like it's about halfway through. So yeah, let's revisit this one once it's ready, and we can see how long that takes. Cool, so that was 300 gigabytes. And the next question you're probably asking is, like, so how does this scale beyond this, right, for very large data sizes? And we've also tried this up to 10 terabytes of data. So here's a 40 GPU cluster running the same exact workload, and we're seeing a throughput of close to 11,500 images per second. And overall, the GPU utilization is over 90% throughout the entire run. So we're getting very good GPU saturation with great data sets and good throughput, even though we're scaling up to 10 terabytes of data and 40 GPU cluster. So just to summarize, we see that array data outperforms SageMaker and Spark for offline batch inference, and overall that using these types of like data processing frameworks are better for this batch inference workload than online inference solutions or trying to roll something out yourself. And array datasets meets all 4 challenges, right? So with Ray, you can easily launch clusters across any cloud provider. It'll scale across this entire cluster. It abstracts away the compute infrastructure management. You can stream data easily from cloud storage to CPU to GPU, utilizing all the cluster resources. It has native support for multidimensional tensors, so you get like zero copy exchange rather than having to go through pandas overhead or JVM overhead as well. And finally, it's fully Python native, so it makes it very easy to develop and debug. So let me just see if this is still going. Yeah, it's still going. Okay. So what's next? If you are doing batch inference, you have some batch inference workload that's running on large data sets, I'd love to talk to you, so please come find me after all the talks. You can also check out the Ray documentation here. It's batchinference.io on how to get started. Or if you want to get in touch with us, you can scan this QR code, fill out a form, and we will reach out to you to help you guys get started with Ray. So we believe we have the most performant solution out there in open source for offline batch inference. And we'd love to work with you to make that a reality for your guys' workload.
And we do have a published blog that actually has all the code in there. So if you actually want to reproduce this, you can actually do that. So we were quite transparent in terms of what's available. And this is not hand waving. This is really experiment that we have conducted. Any questions? Sorry? Talk to me. I think, do we actually have a blog link over there?
No, I don't. I'll add it to the slides.
Okay, yeah, what I'm going to do is I'm going to share the slides on the race, on the community Ray Meetup. So if you've joined us, you will actually get it. So if you're part of the member, you'll get both the recording as well as the slides as well. Anybody else? We'll give a big hand to Amog. We'll have Eric come in next. And like I said, we're going to hang around here, so if you have any questions, let us know. We are here to make sure your batch inference goes smoothly.
Whoa. Okay. Should I join the Zoom? Is that the?
Yeah.
Okay. The invite somewhere? Find it.
Did you send him an invite? Or can I check your email?
Oh, okay. That's what's ID? Oh, great. Everyone's in mute, right? Okay. Cool.
Okay, well, hi everyone. In my talk, I'm going to kind of go over Ray data and this new feature of Ray data called Ray data streaming that kind of powered Amog's talk. And I'm going to cover a little bit of the same material, but I'm hoping from a different angle, especially for those of you wondering, okay, this data streaming is great. How does it actually work? Is it a fundamentally different, and so on. So this talk is going to cover both ML inference workloads that Amog talked about and distributed training, which is another popular use case for Ray data. And I'm going to tell you about this new Ray data streaming thing, which is just recently released actually in Ray 2.4, and how it kind of improves both of these workloads. I'm going to walk through a bunch of examples, and then at the end we'll hopefully have time to go over the back end. So a bit about me, I'm the TL for Ray and open source Anyscale. My primary focus these days is on Ray data and other machine learning workloads. Previously, I worked in a lot of system stuff in Berkeley and other companies. Yeah, so let's dive into ML workloads and data. So at a very high level, I think like kind of data processing comes into ML workloads kind of in kind of a pipeline of 3 steps. First, you have the kind of problem of just organizing your data in the first place. And in kind of the industry companies, it's known as the ETL step, where you just take raw data and you're organizing it into a bunch of tables, maybe your data warehouse and so on. And you need to do this before you're even ready to get ready for ML training. Then you have the next step of like, how do I get my data into my model in the right format, where you do pre-processing. And then you have the actual training or inference where you were doing modeling work. And just to make this concrete, the first step involves stuff like ingesting data, joining tables. Pre-processing can involve things like resizing images, decoding videos, data augmentation, scaling data. And the last step is where you're using your machine learning frameworks like PyTorch, Hugging Face, and so on. And just to kind of generalize here, typically you see like ETL and pre-processing take place on CPU, so running on CPU nodes or maybe a CPU-heavy cluster. And then training and inference, where you really see people leverage GPUs very often for model training. And we're going to focus really on the last 2 steps here. And this is kind of the usual scope of ML team, is also kind of where Ray data is kind of intended to shine. So our vision for how Ray fits into the ecosystem space is kind of segmenting this to ETL and this last mile like pre-processing and training inference step. So for ETL, we kind of don't want to reinvent the wheel. There's like a really mature industry out there with Spark, your data warehouse, SQL systems, and so on. So we think that's fine. That's great. Where we think the ecosystem could be simplified with Ray is in this pre-processing and training step, where the ecosystem is much more fragmented and the needs are much more diverse. So the kind of goal of Ray data is to allow you to write any kind of pre-processing and training inference job kind of in a single Ray program. Kind of no matter if you're training on one laptop or a big cluster, it kind of should all just work in the same way. So a bit about Ray data. I think in the previous talk we mentioned Ray data a lot. It's one of the libraries of Ray. In Ray, we have this Ray Air, which is kind of like a suite of libraries, like a toolkit of libraries for ML workloads, alongside train, distributed type parameter tuning, serving, and of course reinforcement learning. And these libraries are all in Python. They're built on top of Ray Core, which is a lower level kind of general purpose parallelization framework. So that allows these libraries to easily scale. And there's a little bit of history here where Ray data is actually a relatively recent addition, a recent library added to Ray. Like when Ray was initially created, there were actually no libraries. It was just a very low-level parallelization framework. But as we work with more ML engineers, ML teams, we kind of realized like these higher-level libraries would simplify a lot of user needs. So we gradually started adding more, starting kind of more on the research side with reinforcement learning, but kind of graduating to like more production use cases like serving, tuning, and now Ray data. Ray data is about 2 years old at this point. And at a very high level, you can think of Ray data as solving the problem like distributed data sets for machine learning. So a Ray data set is kind of a reference, kind of object that you can use to work with data that can span multiple nodes in a cluster. And it integrates well with kind of industry standards. Like you can read your data straight from S3, written out from Spark and Parquet format, other common formats. Internally, Ray data uses Arrow to represent data, so that makes it really easy to feed it to ML frameworks such as PyTorch, XGBoost, and so on. And there's a lot of APIs. I'm not going to go over the APIs, but a couple of the kind of high-level things that you should be aware of for this talk is you can read data from storage using Ray data read. For example, you can read from a cloud bucket, or you can read files from your laptop. You can transform data in batch. You can pass a function like a Python UDF function, to transform data, and you can consume data in various ways. I think the consuming part is actually where Ray is kind of interesting. And not only can you write data out to cloud storage, but actually with Ray data, you can get an iterator, a distributed iterator of the data. And that is actually a high performance iterator you can use for feeding data into distributed training. Okay, streaming. So streaming is a new feature. What did Ray data do before streaming? So previously, for applying preprocessing, Ray data just used bulk execution. And what is bulk execution? If you're not familiar with kind of the data frameworks, it's kind of like the naive, straightforward way of data processing. So basically, if you have your data pipeline in Ray data, we would load the data to memory, apply all the transformations one step at a time. And if you happen to run out of memory, oops, Ray will spill the data to disk. It'll slow down the execution, but it'll continue. Yeah, and this worked kind of pretty fine for reasonable sized data sets. For example, machines these days have a lot of memory, so if it's a 100 gigabyte data set for ML training, it'll work just fine. It'll just load in memory. But once you scale beyond that, it just kind of doesn't work. Yeah, and this is very similar to Spark's execution model. In the kind of academic literature, it's both synchronous parallel execution model. So what we kind of realized is that for larger scale use cases, really we needed to implement first-class streaming execution. And this actually was implemented and became the default execution strategy in Ray 2.4. It's not an API change, it's purely a backend change. And the idea is kind of instead of executing operators one at a time in bulk, you build a pipeline of these operators, such as read, preprocess, and so on, and you kind of stream data through these operators. And the goal is to like reduce your memory usage, kind of stream the memory, be very efficient, that you avoid slowing down for larger data sets. So kind of a motivating example is where preprocessing is like a big bottleneck is kind of video inference. So imagine you have a model that works on video frames, and you're reading video data, decoding that video, applying your model in batch inference, and saving the results, right? So when users try to do this, they often run into several problems. First, the decoding can be pretty expensive. So you might want to use a heterogeneous cluster. You have CPU nodes in addition to GPU nodes. So that's where Ray data can come in. And another challenge is you have this kind of blow up. Like you decode the video frame. You say you read like 10 gigabytes of video. You decode that video. It kind of blows up to like 100 gigabytes or more of frames. And you really don't want that data to end up like spilled to disk because you end up writing to disk, reading from disk, and it's super slow, right? So you want the data to be streamed through memory. And that's kind of the problem that Ray data streaming solves. The video inference is kind of an extreme example of this. And I use the inference example, but it also applies to training. And let's see how we could switch from inference to training. All you're doing for training really is instead of sending it to the stream to the model, and then saving it to disk, you're splitting the stream up into however many training workers you have, sending it to those workers for doing their model forward pass. So that's really the only difference. The decode part is entirely the same. So Ray data streaming also can power distributed training for like PyTorch, TensorFlow, and so on. Okay. So I want to give a high-level overview of why streaming, when would you use streaming, the benefits, and then we'll dive into examples to make it more concrete. So let's start with a very simple CPU-only pipeline. Like say you're not even using GPUs, you're just using some simple CPU model. With a bulk execution strategy, it's actually pretty good. If you're not working with like GPUs, you won't do any spilling to disk. It's memory optimal, and it's good for inference. There's actually no reason to prefer streaming in this case for these simple pipelines. But it's actually kind of bad for training because you cannot kind of incrementally access your results. You kind of have to execute the whole thing, and if it doesn't fit in memory, it's kind of bad. So streaming does even for the very simplest pipelines help kind of address some needs there for distributed training. For heterogeneous pipelines, such as the one Moog showed where you have both GPU and CPU stages, streaming starts showing even more advantages. So bulk execution, as we saw before, is kind of inefficient, high overhead, whereas streaming is still basically just as good, right? And we actually see both of these. These are pretty common in ML space. Obviously, if you have a second one, you might see more value from ray data streaming than the first, but it's kind of good for both. So next, I just want to walk through concrete examples. So let's revisit our simple batch inference job. Let's say the model is just on CPUs, no GPUs. The data flow is I read some data, pre-process it, do inference from the model, and it's in. In code in Ray, it'll look like this. So I import Ray. Let's say we define our model and preprocessor, define our UDF. So the UDF is a batch of, in Ray data, UDFs are batches of NumPy arrays, and they return batches of NumPy arrays. And I run my pipeline, just Ray data read parquet, map batches the preprocessing function, the model function, and then write. So that implements that four operation pipeline you saw before. And you might think, okay, why is it a single stage pipeline? Why am I calling it a single stage pipeline when it's 4 things? It's because they run on CPU, so the pretty standard optimization is you fuse them into one task. So it's just one task running. So if you bulk execute this, I guess you have like 3 partition of data, you run that stage, you get all your outputs at the end. Pretty straightforward. So yeah, you see the memory is just fine. There's no disk spilling going on. The only thing is it's not great for distributed training. The data's too big. For streaming, the execution is we create the operator and then we can kind of stream data through it. So here you kind of see it's like one block at a time. In principle, the operator could have internal parallelism, could execute a lot of time. And the output is one at a time. And the operator can implement things like back pressure and the kind of incremental returning of results, which makes it suitable for distributed training. Now let's look at the more complex case, the heterogeneous pipeline. So the only difference in this pipeline is the inference operator is placed on a GPU. And how we express that in Ray, as you saw before, is in Ray we have a class. So the constructor is where you create the model, the stateful model, and then we have a call function that you can use to repeatedly call that model. So the model is on a GPU and it's cached. And then the only difference in the pipeline is that we map batches with that class instead of the function. With Ray, you can say num GPUs 1 to set the resources to that, and we can set the number of replicas of that actor. So we can set, say, size equals 10 for 10 GPUs or 10 replicas. So this creates it's like a 3-stage pipeline here. So we have the initial I/O and pre-processing on CPUs, and the GPU operator, and then the output operator. And the reason we want separate stages here is so you can independently scale these things, right? So you might want to place these on CPU machines that are different from the GPU machines. Like, say you just have one GPU machine and 10 CPU machines, for example. So, and visually, the bulk execution here looks like this. You execute this, the data. Now we have intermediate data, so it could be spilled to disk in the cluster. The second stage reads that data back, writes it to cluster storage, and there's third stage would read that data back before writing to wherever it's going. So as you see, there's writing to storage, to spilling, so we can slow down for inference. This is like the main reason why Spark was slower workload before, and of course, it's not great for training. And so of course, with streaming, you don't have this problem. Every operator will implement its back pressure to reduce memory usage. Every operator here can run, say, one at a time. So once the first operator is done with the block, it sends it to the second operator, and the first operator can start working on the next partition, and so on. So every operator runs one or more things at a time, and then eventually you finish, and without exceeding the memory limits of the cluster or anything like that. So no real downsides for these ML workloads. And yeah, just to summarize the comparison with other systems out there, for open source systems in particular, Ray data streaming is more memory efficient than kind of more ETL-oriented data frameworks for these ML workloads. It supports heterogeneous clusters because Ray supports heterogeneous clusters. And this is really because of the execution model, and which is better for inference and better fit for training as well. Another interesting thing is ML ingest libraries. TF data, torch data, Petastorm kind of solve a similar problem for distributed training. The main limitations we've seen is that they're not good for scaling out, and they're kind of a separate paradigm, right? It's not like the same data pipeline for inference training. You have to kind of work with separate systems. That's one reason we see people like want to choose Ray data compared to these other systems. Yeah, it's actually kind of interesting. I think like Meta and Google internally have stuff that's more similar to Ray data, but not open source. I think I have time to do this example. So here's another example of a 4-stage pipeline. And I'm going to use this example to point out some features of Ray data. As I'm going to write 4 UDFs. So here's the UDF to decode the frames. It's very similar to one you've seen before. Here's an annotation actor. Here's a frame classifier actor. So kind of the high-level idea of this pipeline is you have 2 models, not just one. So after you decode your frames, you have one model that annotates your frames with additional metadata, and then you have a second model that does the classification. So it's a kind of a chain of models. And then you finally have the right operator. So when you put this together, I think there are a couple of features to note from Ray data. First is the read binary. So we have good support for binary data formats, not just Parquet and so on. In general, like unstructured data is handled well in Ray data. The second thing to note is that this decode frames, you'll see, has this interesting thing num CPUs for. So this allows you to kind of customize how Ray allocates resources to your operators. So here we're saying this decode frame is really expensive. I'm going to allocate 4 CPU slots on a node instead of 1, so you can kind of limit the parallelism, kind of customize how it's scheduled. And yeah, here we have an actor pool strategy with size 5s and an actor pool. This is on CPUs actually. So you can have CPU actors, and here we're using GPU actor, and we're setting a batch size. So Ray data will also make sure the right batch size is reached for GPUs, which is important. And then we have the output, right? So you can really customize your pipelines. For example, it's very common for models to use much more memory than you might anticipate. So you might want to increase the CPUs for the model to prevent it from crashing, things like that. And yeah, this is kind of a complex pipeline. Ends up every transform is its own operator. First one's running on CPU tasks. Second one running CPU actors. Third one's on GPU actors, and the fourth one on CPU tasks. So Ray data will kind of stitch together this pipeline and run it in the cluster. So you run it, you'll see some log messages showing the DAG that's actually created, and there's a progress bar showing resource limits. So this is actually part of the back pressure. So this is all the limits that Ray data will try to keep the pipeline under. And you run it, then we can look at the outputs. So, and if you haven't seen Ray dashboard, there's also observability tools if you go to the metrics page to see what's going on in the cluster. So when I ran this pipeline, these were the graphs I got. So I think this is a very small cluster, maybe 5 machines or something like that. And you can see here's one graph of active tasks by name. So map batches, you can see, I guess the most active task was this frame classifier actor. There were 6 tasks active, or 16 tasks active on average the whole time. Then the second one was the frame annotator. You can also see the state of the actors. You see after the actors were created, and they kind of stayed busy the whole time the pipeline was running. And you can see the network usage of the cluster. I guess here there are a lot of nodes sending data between the operators. Okay, and an overview of the backend. So Ray data is built on top of Ray. There are no special stuff, it's just using Ray APIs. So it uses Ray tasks and actors for execution of operators, and by default uses tasks, but for GPUs and stuff, you can use actors. The intermediate data is stored in the Ray object store. So, and there's back pressure to kind of enable efficient streaming without spilling to disk. This is kind of a subtle point because like if you don't have back pressure, there's kind of no point in streaming because it's just bulk execution. It's the same thing. Right? So the main difference is just actually the back pressure. And this is kind of interesting. Like, why did we build on Ray Core? There's kind of a lot of stuff we just get out of the box for Ray, like for free. So we have the heterogeneous cluster support, and we get automatic fault tolerance actually. Because we just use Ray tasks and actors, we inherit Ray's lineage-based reconstruction, which means that you're running a large batch inference job, and something crashes, we lose some objects, Ray will just resubmit the tasks, resubmit the actors, and it should survive those failures. And of course, the object store provides things like spilling. If there is, for some reason, unexpectedly high memory usage, like some UDF returns some enormous data array that has to be spilled, then it will just slow down instead of crashing. Right? And there's a lot of other things the object store can also do shuffles. Yeah, and the optimizations from Ray, like for data locality, also kind of automatically apply here. So scalability, we're still early in the scalability test for Ray data streaming because it's a new component. But here's one example of a 20 terabyte array data set that we ran on 500 machines. And we try to sample some simple like 1, 2, 3, 4 stage pipelines and kind of just check the throughput. And you can see the throughput is actually fairly good. So you could do more than 1 terabyte a second on the simplest pipeline. Like there's very little data movement for these pipelines. As you need to send more data across the network, the throughput slows down. You see it still works. And the final feature I want to talk about is a bit more about distributed training. So I mentioned before, you can use these same pipelines for inference and for training. And what does that actually mean in more code? Basically, you're just swapping the latter half of the operator. So like say I have that read pipeline, I'm reading some data, I'm applying some pre-processing, and then sending it to my model for inference. With training, the first two things stay the same. So you have that read data source, map batches. The only thing I change is I'm going to add this split call. So I'm going to add an operator to split it into a number of subset data substreams, and then I can kind of give it to my Ray actors to consume in parallel. This is something that we're trying to incorporate with Ray Train as well to make it a little bit easier to use. We also did an experiment of streaming for training with Ray data. So this is an example where we used just GPU nodes and then GPU nodes plus CPU nodes. And this is actually not even, this pipeline, I think, I should say, it's just reading some images from S3 and applying a pre-processing operation before sending it to the trainer. And you can see that adding CPU nodes actually speeds up the training significantly. Like the training throughput is much higher if you use CPU nodes because the additional like network and TPU from those nodes. Okay, so I think that's pretty much all I had. Kind of TLDR's Ray data scales both batch inference and training workloads. It's kind of inherently more efficient computation model than bulk processing. And the APIs lets you kind of compose these things simply. So we have the docs available in docs.ray.io. Coming next is we're improving Ray Train integration in 2.6, and we're trying to harden it to work more robustly at larger scales. For example, hundreds of nodes and very large numbers of the input files and so on. And yeah, if you're interested in working on these, we're happy to kind of collaborate.
Thank you, Eric. Quick question. What does an operator comprise? Can you go back to a code and say, is the operator the function, the user-defined function that you provide to the map batches, or the operator is something that Ray data fuses together into one operator?
Yeah, that's a good question. I think it's a little subtle point. What is an operator? Is this an operator or is this an operator? The terminology I think we have is this is a logical operator and this is a physical operator. So like when you define an API call that creates a logical operator, and then rate data will optimize and create these physical operators that might involve multiple fused logical operators.
So the concept of operator is actually something that the ray data does behind the scenes. It's not that you define as an operator. You define the stages of the things you want to do, and the ray data, when it's actually parsing the code, fuses that into a single operator that actually makes sense to execute.
That's right. Like as a user, you write transformations on the data source, and the term operator isn't actually in the API. It comes out in kind of like the log messages and the status reporting. It's been more of an implementation detail. Yeah.
I couldn't help but to see the analogy, and maybe I'm wrong over here, but when you use the word like staging, because if you recall, obviously you come from the Spark background, the way the Spark takes a job, converts into a stages, and stages then converts into a task. Is that very similar in how you're actually parsing the code to divide them into stages, and then from the stages you're actually executing things in parallel?
Yeah, it's pretty similar. Actually, I would say before the streaming backend, it's like pretty much the same execution model. Yeah, it's a bulk synchronous execution.
Okay. Any questions? I'm going to open up to the crowd. Yeah, here you go.
Does the ray data also support some kind of an SQL translation, like these operators and the stages kind of a thing?
Yeah, so does Ray data support SQL? So we don't have any first-party support for SQL. There are actually some community projects for running SQL on Array. So I know of a lot of experimental like data frame libraries on Array for running SQL, and you can also run actually Spark on Array. Actually, I think some companies actually run that in production, like Spark on Array to kind of like unify their infrastructure.
There is an independent community project called Ray SQL, which underneath actually uses Ray data, right? Any other questions?
I had a question regarding the heterogeneous pipeline, just trying to understand it better. So essentially when you have a task that gets completed on a CPU, are those CPUs on the same node as the node with GPUs, or are they separate nodes? Because then communication patterns become very different and performance can vary.
Yeah, so the question is, if you have like the CPU stage and the GPU stage, like what happens if they're on different nodes, or can they be on different nodes? So the answer is, yeah, they can be on different nodes. For example, you have one GPU node, then it might make sense for Ray data to schedule these on different nodes. And Ray data has this optimization for locality optimization, where it will try to put them on the same node. But if it wouldn't, like if there's not enough resources, it will put them on other nodes, and there might be network transfer incurred to transfer the data between nodes.
In one of your examples, you say you can specify how many GPUs you use to run the inference operator. And I'm wondering, can you also specify like a GPU type if you have like a A100 or V100, and then you want to say which one you want to use?
Yeah, a good question. So let's say you have a cluster with two different GPU types. So Ray has this notion of like custom resources. So you could like kind of tag nodes with like custom resources, and then you can add that to a constraint. I think I have probably some example of that. Like here we're saying num CPU is 4, but you can also add like resources equals like custom tags on a node, so you can make sure it runs on a V100 node. So yeah.
Yeah, custom resources allows a way to provide an affinity that this particular task is going to be scheduled on that particular GPU or a CPU. Any other questions? Here you go.
Thank you. This work reminds me, how Spark outperformed Hadoop. When you avoid, writing on the disk. Anyway, but when you compare the 1 stage, 2, 3, and 4 stages, it's not clear if you are just using CPUs, GPUs, you are mixing. So.
Yeah, good question. So for like kind of the stress tests we did, that's a question, right? This one. These were very simple stages. So these were all actually all CPU actor stages. And it was run on a CPU cluster because it's like a 500 CPU node machine. So what this is doing is actually it's testing the scheduler, it's testing the data plane. There's no GPUs involved.
So there is a lot of communication. That's why we are losing the performance.
So one is there is some more network overhead. Like so, RAID data has this like locality optimization. We try to avoid data movement, but as you have more stage, there will be some more data movement. And also the number of tasks you have to dispatch is just very high at this scale. So the scheduling, the actual control loop starts becoming a bottleneck at this scale.
So each stage is executed on one machine or a different machine or?
Oh, so yeah, I should give more details about this. So imagine like this like 3-stage pipeline. Like every stage will have like, there'll be 3 operators and every operator will have, I think it was like 200 actors or something like that. So it can have up to 200 concurrent tasks per stage. And these actors are spread across the cluster.
Yeah. Because I think you can have better results if you, with some tuning, you can, have better throughput. Anyway, just.
Yeah, I think I agree with you. Like, so this is stressing the upper boundaries of our scheduler, and we haven't bothered really optimizing the scheduler. It's like a event loop written in Python.
Yeah, my intuition is you can do better.
Absolutely, yeah, I think so. And if you have a use case where you need it, yeah.
Enthusiasm. We are hiring, by the way. Any other questions? Give a big hand to Eric. And last but not least, we actually have a Ray user case from Pinterest, and he's going to show us how they're actually using Ray to build the internal platform interactively to expedite their developer experience. So please welcome Suwon.
Let's give it a try. Zoom.
Share your screen.
Screen.
I to give permissions or something.
Yeah. Rejoin.
All the hooks you have to jump through this to get that thing.
I think I should be there. Let's see. All right. Got it. Share screen. All right.
Yeah, I can see it.
All right, cool. Hello, everyone. I'm Sewon, and I'm from the machine learning data platform team at Pinterest. Thanks so much for having me here today. Today, I'll be talking about improving ML dev velocity with Ray at Pinterest. So hopefully this is something that you find interesting. Today's talk is going to be a little bit more high level. We're not going to have a deep dive into the performance benchmarks and how we're squeezing the most out of the hardware using Ray, but we're going to take a slightly different angle and talk about machine learning engineer velocity and how we think about making machine learning engineers move faster So as we go through this talk and hope you put yourself in as an ML engineer's shoes working in a web scale recommendations company and see and really follow through on how you might be able to develop models faster. All right, so I'm going to start by giving a very brief overview of machine learning at Pinterest, what kind of problems we solve, at what scale, what kind of metrics we care about. Then I'm going to talk about one of the most popular developer interfaces in machine learning, which is workflows. And then we're going to talk about an interesting limitation that workflows have, which we call the scale first and learn last problem. And then we're going to go into how we are using Ray, how we're thinking about using Ray going forward at Pinterest to switch this around to learn fast and scale fast. And then I'll be sharing some asks for the Ray community. All right, so let's get started. So first of all, machine learning at Pinterest. In case some of you may not be too well versed with what Pinterest is, it's a visual inspiration engine. People come to Pinterest, and our mission is to bring everyone the inspiration to create the life they love. People come to Pinterest with various intentions. Some of our pinners might be looking to revamp their house interior, or look for new fashion, look for new recipes. And they're trying to do stuff in real life and look for inspirations online. And that's where Pinterest comes in. So at its core, it's a big recommendation engine. Right? And this recommendation engine is powered by a variety of machine learning applications. When you first open the Pinterest application, you will be shown the home feed. That's where our very first recommendations show up. You like some of the pins, which is what we call our content. You click on them, and it's going to take you to a variety of other related pins. You can also search for pins using text. You can perform image-based search. And between various recommendation types, ads will be interleaved, where in an ideal form, the ads are so relevant, we know exactly what you're looking for, that it's hard to distinguish them from organic content. Right? And a lot of these product features and surfaces under the hood are also then further powered by other types of machine learning applications. We have image understanding, content understanding. LLM's a big thing, right? We have a lot of good LLMs and maybe visual models under the hood, extracting content and summarizing them under the hood. We also use them for unhealthy content detection. Right? So these are all very important machine learning applications that power this recommendation engine called Pinterest. So, and we do this at a very large scale, and that's where interesting problems start popping up, right? And we have 450 million monthly active users, exploring corpus of over 100 billion pins, generating billions of events every day. A variety of machine learning use cases in terms of how the problems are formulated. There's a recommendation and ads problems. And within those, there's retrieval, ranking, and blending machine learning problems. I briefly mentioned representation learning. Got to understand the content, understand the user, and really help them do the stuff they love. And these are, as I showed, scattered across all sorts of different product surfaces that I just mentioned. And this is powered by a centralized machine learning platform, where our goal at a high level is twofold. Right? First of all, we want to build foundational components with new capabilities. And these are things like feature store, training compute platform, inference services. But we also really care about our machine learning engineers. In the industry, people talk about it's so hard to get GPUs. GPUs are so expensive. But if you look at it from a business perspective, machine learning engineers are more expensive than GPUs. And we really care about helping them move faster. This is the resource that we want to optimize for. And that's going to be the center of my talk today on how we are thinking about improving machine learning developer velocity. And from a rough, very high-level point of view, we break it down into two metrics, calendar days taken to perform a certain task, and then the active development time taken to perform certain machine learning tasks. All right, so as we go through the talk, please keep in mind the angle that we're approaching from is optimizing machine learning engineers. All right, so now let's go into the main body of the talk, machine learning pipelines and the scale first and learn last problem. So, empowering web scale machine learning is a very hard thing, and by now I'm sure a lot of you have seen this diagram before. It does a really good job in demonstrating that writing machine learning modeling code is a small part of the entire machine learning lifecycle. Right? You got to collect the data somehow, you got to verify them, extract machine understandable features, and then you got to analyze them. You got to manage resources, manage the pipelines, and you have the serving infrastructure and so forth. It's really, really tough, right? And I particularly like this thing because it makes such a clear case to our business leaders on why they should be signing our ML platform paychecks, right? This really shows how complicated this space is and why we should be investing it to help machine learning engineers move faster. And when you have a lot of these steps, right, it's really natural. The first thing engineers think about is, okay, you got to do a bunch of stuff. Why don't we connect them as workflows? Right? So then in this kind of model, we have ML platform teams jumping into the scene, building some foundational components, feature store, data sets, hyperparameter tuning, training platform, model store, visualization, and inference solutions. And each of these foundational components end up exposing APIs or even jobs that run on popular execution runtimes, right? They can run on Spark, they can run on PyTorch, they can run on Ray. And this is the very first layer of operation for our machine learning platform teams. We build the components are programmable, right? Once you have stuff that's programmable, you gotta figure out how to orchestrate and glue them together. And then we talk about how are you gonna do that? And most companies use something similar to Airflow or some variants of their workflow systems where you can say, hey, I gotta perform this step, that step in that order, and I wanna be given some visualization and some operational tooling. Right? And this is a somewhat realistic view of how a lot of machine learning pipelines are structured at Pinterest. Once you start gluing these things together, and Eric actually earlier touched upon this in a little bit more of a higher level view, where many ML application teams have a somewhat fairly static workflow that's continuously producing data sets. In our case, it's recommendation heavy. So we need to join stuff that we served, a lot of features, and the stuff that users did on our application. You join these two, and then now we have a training data set for some large-scale supervised learning. And then we move on to the actual training workflow. And this is what we call the inner loop of the ML lifecycle, because this is where machine learning engineers iterate. This is where they interact with the most and start bringing business value. And this is also fairly realistic at Pinterest, where one of the very first things you do is try out new features. Right? It's not there in the training data set. Somebody's publishing a new feature. I'm going to try it out. And then, okay, I enriched my data set with a few features. I'm going to run some new sampling strategies. I'm going to run some new split strategies. And then you apply some reward algorithms to assign weights. And then you understand the feature stats. Then you got to train. You got to evaluate, run some feature importance analysis, and then you promote the model to some model store. Right? And that part is the inner loop, and that part is what we're interested in optimizing, right? And when we think about optimizing workflows, the very first thing we think about isn't really about, okay, how can I make individual things faster? The very first thing we think about is, are people doing the same stuff over and over again, right? And just like how we refactor code, there's rule of three. You find yourself doing the same stuff 3 times, you're going to refactor, pull it out into a function, and then make sure that you don't do it again. Same principle applies to MLOps from platform teams, where we, instead of refactoring code, we templatize the workflows so that if we know that people are going to be following a certain structure to train models and solve some business problems, we're just going to give them configurations. Somebody's written it, why should anybody else write the same thing over and over again? If I've written this workflow, I want to try learning rate 0.1, and my colleague wants to try 0.2, we should be using the same stuff and just plug in 0.1 and 0.2, right? And that's the principle behind it. And this kind of workflow templating strategy really improves ML developer velocity and bring further values, right? And there's a lot of different steps in this pipeline, and it's reasonable to think that every step is producing some form of data variance, right? We don't want people to be doing running the same stuff over again. It's not just about writing code. You gotta be able to cache the data, and if it's no longer important, you gotta be able to garbage collect it. You gotta make sure that these intermediate data sets are discoverable. You wanna be able to deduplicate them, from lineage tracking. One of the more important thing on top of developer velocity is reproducibility in machine learning, right? When we templatize workflows like this, a model is now then defined by it's some function of shoving configs into some template, right? And this becomes highly reproducible. You don't have to figure out, oh, which data set did you use? Oh, wait, how come I run the same thing while I'm not getting the same result? Nobody needs to worry about that anymore because all of your experiments, hypothesis, and validation is defined by a tuple of configurations and templates, right? And it really helps that these configs are declarative. It's like you go to a lab and you have some kind of experimentation plan and you can reason about what's going to happen, right? So at Pinterest, we built some lightweight workflow wrapper. So we call it the ML workflow templatization system. It's called EasyFlow. Here's some realistic screenshots and code examples. That code example is somewhat fake. Basically, we give the ML engineers or platform teams some tool to write some Python program. And in the Python program, they're saying, hey, this function is a template. I'm going to define a bunch of configurations. And what the system does, it just renders some UI form fields so that once somebody has written and did the job of writing the pipeline and templatize it, anybody can go and just plug in some configurations and then gets value out of it. Right. And also, as you can see here, it performs some deterministic lineage tracking and does a few fancy stuff out of it, right? If two ML engineers are kicking off the same stuff and they're evaluating the exact same sequence of lineage of data and jobs, it's going to perform some runtime synchronization. It's going to lock it so that, hey, somebody else is doing the same thing. I'm not going to let you do the same thing. Let's wait a little bit. Or they can also deduplicate the jobs and data sets, automate the data set management. As I mentioned, once you start tracking the lineage, things are even more reproducible than before. All right. And this is also one thing that the templating approach that we particularly like from ML platform teams is that it doesn't have to be ML platform or infra teams going ahead and building this plumbing work, right? Anybody can go and write domain-specific templates. So anybody can do, if they have time and want to do plumbing work, go do the plumbing work, and you come up with this kind of the templates. You can release it, see if the community likes it or not, and then you can get some feedback and further democratize machine learning in the company. So let's see now. I want you all to think about, you put yourself in ML engineer's shoes in this kind of world where such an approach exists. Let's talk about one case here where you're trying to train a new student model using a different teacher model. In production, there's a student model trained, running, but it was trained on some other teacher model. I want to plug in a different teacher model. And then here's what an engineer needs to do. And it's only going to take maximum a few hours. So first of all, you just got to find the template that you need. Go to the UI, there's a drop-down, search for some template. And then you can clone the configuration from the model you're trying to beat. You clone that thing, and then you plug in a different teacher model, and maybe you want to try some other configuration, right? And then you change a few things, click save, the workflow gets scheduled, and it starts running periodically, refreshing the model, and then you like it, you like how the model's performing, and then you can go and take it to an online A/B experiment. And here in this workflow, or in this developer flow, you just need a few hours, maybe a few minutes, or maybe a few hours if you want to make some minor changes to your training script. But that's all it takes to push a model. All right. And with this kind of approach, we're juggling hundreds of petabytes of training data across our machine learning applications. We're running 1,500 workflows every day, spanning across 3,000 training jobs every single day, right? And ultimately, this is because if there is a template, you can just go and try out new ideas, and that means we are improving machine learning developer velocity. What that means is people can train more models, try out more ideas, and then you can see more improvement, and it's going to be good for the business. Right? So now let's talk about a different case this time, where I'm a machine learning engineer, and I want to try a new weighting algorithm. Right? It's an algorithm that nobody's tried before. I want to try it. I have an intuition it's going to work. And this specific case takes a lot longer. And we're still operating with this whole templating engine and infrastructure and everything there. Let's see. Nobody has done it before, so I still got to go write a job. Right? It's going to be a big data job. And oftentimes, I have to write it in Scala Spark. And Scala, although I love it very much, it is very hard to learn and pick up over time, right? And people say, oh, can I just write PySpark? Sure, you can, but if you're going to be doing a lot of row-heavy operations, you don't want to do it in Python, you maybe want to do it in JVM, right? And then this, although we hate to admit it, it is one of the most effective forms of development. You just kick it off and kill it, kick it off and kill it, and until it works, right? It's just part of development. You got to test it, unit test, integration test, and you run it in testing environment, run some data validation, and then now, okay, you're satisfied with the job you wrote. You got to go and integrate that with the workflow template, write some new airflow operator, new if-else logic branch, and you got to tunnel through a new configuration parameter to the template. And then unit test it, integration test it, and then you land the code. Obviously, it took a lot of time for us to get there. You probably had a bunch of meetings in between, which further slowed you down. All right, and once this thing lands, go through CI/CD. Now we can finally go to the templating engine and kick off the workflow and test the idea that you wanted to try, right? So something's not right here. Obviously, there are different approaches. You can just manually glue things together. You can write a bunch of Spark SQL queries and write some data. Data test 0 here, data test 1 here, and then juggle them manually, maintain a spreadsheet. What did I do here? What did I do there? And you can actually lose reproducibility and iteration speed. Why are we losing iteration speed? Because you're not end up just going to want to try one reward algorithm, right? You're going to have an intuition that there's this sort of direction is going to work well, and it's a space of algorithms. You're not just going to want to try one. So you're actually losing both. But actually, a super popular approach is to file a ticket to ML platform, tell them what you want to do, and you're going to revisit the idea a quarter later or next half. You're going to have more meetings, and ML platform team's going to have to reroute resources in improving stuff in different parts of the stack. So these are some alternatives, and that's why ultimately we just have to go through all of these steps. And this is what we call the scale first and learn last problem, right? So what's happening here? It's just a classic challenge with templating. Whenever you template stuff, machine learning especially is something that changes super fast, and templates inherently reflect our understanding of the past. Sure, there will be really intuitive engineers who can foresee the future and see, okay, I know I'm gonna try a bunch of these things so they can create some templates for it. But ultimately, it's a refactoring process, and refactoring is done on existing code, right? And here we are trading off reproducibility at the cost of developer velocity. And as you saw in the two cases, there's over 100 times difference in developer velocity. Sure, we're doing different things, but still, we cannot argue that the engineers are moving 100 times slower. Right? So we really want to solve this problem. As I said, ML engineers are more expensive than GPUs, right? So, and we want to look at where the bottlenecks were. This engineer was juggling through so many different languages, Airflow in Python, and you go Spark and you learn Scala. Maybe you want to leave it with some Spark SQL stuff here and there. And then you also have to learn a lot of runtimes and frameworks. Airflow, Spark, PyTorch, and the in-house libraries tend to be the worst out of these. And you go through code reviews, wrestle with the build system, meetings, and most importantly, development is not interactive. Kickoff, kill, that's how a lot of people develop, and that we need to fully embrace somehow, right? And these are some of the bottlenecks that we identify. The reality then is that Renaissance ML engineers who are so good at doing everything, they are good plumbers, they know how to model, they have intuition, these people can move fast. But most of us are not Renaissance ML engineers, and we are all going to be moving very slow, and that's bad for the business. So then let's talk about how we are thinking about using Ray and how we've been chasing the road of solving learn fast and scale fast problem, right? We're trying to switch it. So looked at bottlenecks, we convert bottlenecks into requirements. That's an easy way to set a roadmap. So we want the developer interface to be interactive. I keep emphasizing run it and fixing it is an inherent part of development. We have to embrace it. We want less languages, less frameworks, and we want shorter, simpler pipelines, right? So then now let's translate that to the user experience. North Star we want to shoot for is some ML engineer can express data processing, training, inference, evaluation, analysis all in one language and one framework, which is then testable interactively and productionizable as workflow templates. And this is the North Star we set for ourselves, and we were looking around very hard and then enter Ray. Right? And the idea then is that using Ray, and I want you to quickly remind yourselves of what Eric was talking about earlier and some of the diagrams, right? The idea is to express the ML ops life cycle as Ray pipelines instead of Airflow workflows, right? Instead of Airflow, you want to do Ray dataset pipelines. Instead of writing Spark jobs, SQL jobs, and et cetera, we want to write Ray tasks and actors. And that's not it, and that's not all of it. There's a lot of really good stuff that comes out of it. Now, Eric talked about stream processing earlier. It greatly improves developer velocity. Think about, let's say we have 3 jobs, or we are clever and we merge that into 2 jobs. We still have to process billions of rows, hundreds of terabytes of data, finish one job, and then move on to the next, and then move on to the next. And then finally, our model's going to see if it likes it or not, right? By converting into streaming, going from that ideation to actually letting your model taste the new form of data is super fast. And that's exactly what we want to save developer time. Also, Eric talked about being able to manage a heterogeneous pool of resources. It's really important that when something doesn't work and it's dying out of memory, we can just blindly throw money at it and horizontally scale it. Because we don't want machine learning engineers waiting around to figure stuff out. They're more expensive than GPUs. All right, and we can also, if everything is in the training, everything can be orchestrated interactively. It means we can run hyperparameter tuning. Right? There is a really big space of downsampling algorithms out there, really big space of reward algorithms. And can we just come up with some intuition, identify a few, and run a hyperparameter tuning on them? That's exactly also going to allow us to help improve machine learning developer velocity. And kick it off and kill it can also then be supported by connecting Jupyter. So we tend to think about Jupyter kernels running in some physical resources, but what Ray allows us is that Jupyter just becomes an entry point that can connect to a larger pool of resources, and that's also some good stuff that Ray enables us to do. Then we want to challenge our idea, right? Is it really realistic to replace workflows with Ray? Probably not, because workflows are not only about scheduling and just gluing jobs together. They allow us to cache intermediate data sets, make them available for reuse. You can reproduce things, and we can retry things easily. ML engineers will ask, hey, if I put it on Ray dataset pipeline and somebody has done it before, am I going to be doing the same stuff over and over again? Now, if one stage of the pipeline fails, do I have to start all over again? Or will Ray application require some kind of a super key to tap into all forms of data sets out there? These are all really important and valid questions. But most importantly, as developers, we have to think, okay, do I go and enrich Ray dataset pipeline with workflow-like functionalities and reinvent a bunch of wheels, right? So we've been thinking about this problem, and we think that it is a solvable thing, which is there is a way to get the best of both worlds, right? And the idea is that, you know, from Eric's presentation, we looked at like tasks and operators and actors and whatnot, right? And these are individually defined reusable building blocks. And if we actually, and once we have a bag of these building blocks, stitching them together or chain of them or splitting them apart is not that hard of a problem, right? We can stitch them together and run it on a single Ray application as one streaming pipeline. Or we can be a little bit more clever and say, okay, these ones I want to stitch together into one Ray job. Those two I want to stitch together. This one I want to be in a separate job. And then what that is just going to be a training workflow template, right? Either we run it on Ray or we orchestrate using Airflow. And it really works out nicely because we platform teams don't want to do a lot of work. We want to delegate to ML engineers. And then we can maintain the shared pool of SDKs where ML engineers are contributing to. Once somebody has done it, it should be discoverable by all the hundreds of ML engineers out there. Right? Now, the second challenge when we think about replacing batch pipelines is it really realistic to replace batch jobs with Ray dataset pipelines with stream execution? And I want to point you to one step, the first step of our inner loop. It's a very relevant problem. It's called feature enrichment or backfill problem. As I said, it's very common. One of the most interacted knobs in ML is to try out new feature. It's the first thing we're going to try. And it's such a fundamental part of machine learning development. And at Pinterest, where you train on months and months of data, and that's logged over time, just to try one feature, you don't want to wait around for 100 days until it logs and fills up your training data, and now you can see if it works or not. If it works, great. If it doesn't work, well, how are you going to clean it up? You wasted a lot of time, right? And feature backfill or enrichment is inherently a join problem. We have logged training data set, hundreds of terabytes coming in. And we also have features from feature store, which isn't going to be as large as training data set, but it's still pretty large. Right? And then the question is, okay, can Ray do this? Is it feasible for the Ray streaming executor to do this kind of joins? And turns out that it is. Right? And the idea is to perform feature backfilling through storage partition join, and this is the one that's commonly known as bucket joins. And we're going to be using Iceberg to partition the data into a few deterministic buckets, right? And you can think of this pre-bucketing of data into as if we are linking shuffle stage all the way to the storage layer so that we're pre-shuffling the data since we already know what the join key is going to be. And we can skip shuffle and perform streaming joins, and we can benefit from the streaming executor that Derek talked about. From a very high level, here's how it's going to work. We're going to write a custom data source. It's a nice abstraction in Ray data. It allows us to spawn whatever read task that we want to spawn. And each read task will be assigned a bucket ID, and training dataset and feature store are going to share the same bucketing scheme. And then we can say that the read task isn't going to perform any form of shuffling. Ray's good at shuffling, but we're not going to do it because we want everything to be in a streaming fashion. So retask is going to go through the buckets, load files that belong to the same bucket from left-hand side and right-hand side, perform in-memory join, yield it to downstream of the pipeline. It's just going to keep doing it, right? And this is how we are going to be performing joins in Ray streaming. There's no magic way to skip shuffle if we don't start leaking stuff into the storage layer, but we are going to be making this happen. So with these two things in mind, here's what the new user experience is going to be for stuff that nobody has tried before. Let's go back to the new reward algorithm, new weighting algorithm, right? I'm going to connect as an ML engineer. I'm going to connect to Jupyter and then connect to a Ray cluster. I'm going to express whatever new algorithm is in the Ray task connector, right? I'm going to then interactively train experimental models, evaluate them, and test my hypothesis. As I said, the space of algorithms is massive. With intuition, I should be able to interactively trim it down and read away stuff that's not going to work. And then I'm going to commit the code for this whatever new task connector that I created. And the platform should be able to figure out how this is going to be integrated workflow template. As I said, once you have task connectors, it's not that hard to figure out if I'm going to compose one job out of it or multiple jobs out of it, right? And then you can now then just go kick off workflows using the templates. Now, this is the North Star user experience we're aiming for. And we hope that the velocity variance will be greatly reduced from the 100x that we saw before to hopefully something that's a lot less than 10. Right? And all of this is from having one language, interactive development, and all the good stuff we talked about Ray earlier. So our progress with adopting Ray and some future work, we rolled it out to one large-scale ranking use case. This use case is doing a couple things, leveraging Ray dataset pipelines, right? We're performing map-side join, but this isn't about for feature backfilling just yet. We're going to be working on it later. But this is for filtering out events that happened that were generated from bad actors on our applications. We don't want the models to learn bad behaviors from them. And we also were doing on-demand downsampling. Right? Downsampling is a very good, it's like building a curriculum to teach your model, right? You want to emphasize certain things and hide certain things away. And this thing should be doable on demand just by writing some Python code. And it's been very helpful because, yes, doing more stuff in the trainer will slow down throughput. That's just how it's going to work. But once we start observing slowdowns in training throughput, we can add one machine, a few more CPUs, and horizontally scale the data processing portion of our training pipelines. Right? Then our plan is to expand to 5 or more use cases in H2. Future work, exciting stuff that I talked about earlier, all fall in here. Right? I think we've proved that it's going to work, and we're going to aggressively chase this down. On-demand feature backfill, we can actually perform a variety of applications that might require joins. Some downstream reward calculation, user sequence experiments, and then we also will be investing in the dataset pipeline to workflow translation. They are homomorphic. So to summarize, Ray allows us to solve the scale first, learn last problem, flip it to learn fast and scale fast. We can express most of the big data processing in Ray and connect them as Ray streaming pipelines, the good stuff I talked about. And then ML engineers will be given one tool. They can focus on writing tasks and actors. And so this is a summary of Ray at Pinterest. And now I just wanted to end it with some suggestions and ask for the community. There's a lot of creative ideas at Pinterest that's going around, but I just picked a few. Our engineers will be giving a talk at the Ray Summit later this year. I'm sure by then we'll have even more good suggestions, right? So, all the good stuff, too many of them. But here's some very high-level suggestions that could make the dataset pipelines even more powerful. First of all, it might be a little bit more contentious, but we believe that in order for us to leverage Ray dataset pipelines more for what was traditionally ETL workload, We really need to invest in data frame-centric APIs. And we want to fully hide, if possible, right? Concepts like blocks and tasks away from the end users, because once you start working with data frames, you really shouldn't be thinking about this, and we want it to be as declarative as possible, right? And can we have some kind of distributed data frame abstraction? I've been starting to see this in some other open source projects. Recently, I came across this project called Daft. Right? They try to have this distributed data frame abstraction. RayDP is another open source project that I was looking at, which tries to layer PySpark APIs and run it on Ray. But we'd love to see something mature, something that's endorsed by any scale before we adopt something. And also I talked about Iceberg and storage partition join. Yes, we're going to prove it. We proved that it works and we're going to scale it out. But what if it was a formally supported API in the Ray data stack? A few also points on user experience, right? Once we start looking into using Ray for more pipelining, there's got to be some dedicated UI for pipelining, right? Eric showed you some of the number of tasks and how they scale and work over time. But, I hate to bring in Spark here, but it shows the steps and what's happening here, how much did it process, and what the throughputs were. Now, once we start visualizing this, can we automatically detect bottlenecks and flag it there? Can there be some kind of like a Dr. Elephant-like interface, right, or experience? And I hope this one's simple, but I think this is actually going to be a killer feature, right? Can we just inspect some samples on demand and see if my pipeline is doing the correct thing? And these things would make the developer experience a lot better. Another thing from my team is, can we have replayable UI logs? Yes, we're biased by Spark, but Spark, you can have the Spark history. You can spin up the UI server later and replay it and see what happened over time. Maybe if we had something similar for Ray, that would make debugging a lot easier. There can be a lot of creative solutions here when we think about how to help ML engineers save their time in the debugging space especially. But so that's some of the suggestions or asks we have. So that's it. Thanks so much, and we can open up for a Q&A.
Thank you very much for the very well thought out pipeline, so stages of the problems. What are we trying to do? How Ray can actually fit in, and some very valuable insights in what are some of the things that we can actually improve to make sure that it addresses some of the questions they actually raised for the Ray community. And I'm sure our developers over here, including myself, so we're going to make sure that we pay heed to it as we constantly talk to you on weekly basis. So I'll open up the floor if you have any questions for beautiful things to do it. How many use Pinterest every day? I know I do. I mean, I go for design and stuff. But any questions for Siwan? Yeah. Do you want to catch this?
So I'm curious. I don't know. I want to know what implementation of everything, like of, the experiments you've run, of the jobs you've run. I just want to know what's the eventual user end state that is beneficial.
Let's see. Yep, the end state is something like this, where I envision a bag of tasks in our code base, where there's the APIs for the tasks are automatically generated, and the gluing of them is treated as a pure infrastructure problem. And I can declare the sequence of tasks to get something done. Is that what you're looking for?
Okay, so you're just processing images, right?
Oh, no, actually. Maybe I could go a little bit deeper into the variety of tasks.
Yeah.
So that this kind of pipeline view that I showed here is primarily with tabular data. So these are actions that users took on Pinterest that gives us valuable signals on which contents are better than the other ones. So they are tabular data. And let me give a very high-level problem formulation. Every ML application is going to be a little bit different, but the problem formulation is going to be given a user U with a bunch of features. When I show this pin with a bunch of features, what is the likelihood of engagement? And you're going to have a bunch of user features. You're going to have a bunch of content features. And then in a supervised training setup, you will have, did this person click this or not? Hide it, like it, save it. And those are some of, and that's what I meant by supervised learning training data set earlier. We do have a lot of image understanding ML applications as well. They're not going to quite fit well with this sample structure that I shared here. But today, you can consider that I'm primarily talking about tabular data, which are logs of user activities on Pinterest.
Simon, can you go back to the SDK slide?
Mm-hmm.
So this is the ML platform SDK stack that you were actually developing in-house, correct?
Yeah. So
Yes.
we're not here yet.
No, I know.
This is the North
But
Star.
that's your North Star. And I think when you mentioned about that you wanted Ray data sets to be more, APIs to be more declarative, where you're telling it what it needs to do, I'm assuming that what you're implying is that these particular SDKs will be declarative in terms of here's a sample task, and that will be converted in its equivalent Ray map batches task, which will go ahead and either do the stages. So you don't have to worry about the stages and all that. Ray should take care of it. But the high level, this is where you actually want the declarative APIs to be translated into Ray stages and task. You don't have to worry about it. Or your ML engineer who is more expensive than GPU doesn't have to worry about that.
Yep. So yeah, if you crack open each individual task or actor implementation, it's going to be imperative. But the way users ask us to glue these things together can be declarative.
So what was the reaction internally when you say, well, you don't have to use Scala, you don't have to use SQL, you don't have to learn all these languages, all you're going to do is in Python. Were they relieved, or were they saying, oh my God, why should I just invest only in one language?
This is a great question, and nobody disagrees that when you come to them saying, hey, we're going to help you only work with Python, nobody's going to say, don't do that, right? There will be people who are saying, but what are we trading off? And that's the more important question. We will be trading things off, right? So, and that's why I was asking for more of a distributed data frame API, because when people author tasks and actors, they are exposed to system level understanding. So we are, let's say today somehow we wanted to make a magical transition to PySpark to, let's say, this kind of world. We are giving users a lot of knobs, right? And that is a trade-off that we would be making today. So we're waiting to see how Ray evolves, how Ray data evolves. It's a really exciting space.
Any questions?
I have a selfish one. What about, are you guys looking into spatial computing and three-dimensional data at all? Yeah.
Sorry, could you say that again?
Are you looking into GLTF file formats yet? Like, are you guys envisioning a Pinterest world where three-dimensional assets are a new marketplace or a new inspiration engine?
That I am not, I don't think I can comment. Mostly because I don't know. I'm sure there's a lot of creative stuff going on in the ML engineers' brains.
Anybody wants to take a last question? Going once? Oh, there you go. Hey, Jan.
So if I understood correctly, you're estimating a 10x productivity increase.
Yep, that's the
Okay.
goal. Mm-hmm.
So have you thought about taking that productivity increase by the number of engineers and the cost of engineers, so that when the executives come and say, what are you guys doing? The CFO says, what are you doing with all this money that I give you? You can say, well, I just saved you X amount of money. Just a thought.
Oh, yeah, definitely. It's going on my performance review package.
We'll give a big hand to Sowan from Pinterest. Thanks a lot for sharing us your initial journey with Ray, and thanks a lot for sharing us, giving us feedback and sharing with the community as well. I want to thank Amog and Eric for giving us an insightful talk about Ray data, and my friends Eric and Diana, they're all gone. And thank you all for coming. And tomorrow we have another meetup, so if you like our HQ headquarters, please come by tomorrow to find out about how you can actually scale and put LLM applications in production. We have a CEO and a co-creator of Ray who's going to be here. The creator of LangChain is going to be here. The creator of Vicuna from Berkeley is going to be here. So you're going to have an exciting panel and quick lightning talks to find out how Ray fits into this grand scheme of things called LLM and foundational models. So hope to see you tomorrow, and thanks a lot, and safe drive home again. Cheers.